we have two themes today. The first is ionization energy. The second is electron affinity. Ionization energy relates to the energy required to remove an electron. Okay? Its definition, it's calculated as the amount of energy in kilograms required to remove 1 mole of electrons. Okay? So if you get values, they'll be in kilojoules required to remove 1 mole of electrons. One odd bit is the calculations are always done in the gas states. You're going to see some states that you're not used to. A metal, you'd expect it to be a solid. But to do these calculations, you could take a laser and vaporize it and make a vapor out of it and then use that metal vapor to do the calculations. Okay? So if we look at the first ionization energy, and I'm going to use aluminum. Okay? I'm going to go IE1 to represent ionization energy, and it's the first electron, so hence the subscript 1. So what this looks like equation-wise is aluminum, but not in the solid phase. It's been vaporized. Okay. We're talking about removing electrons. We'll see a lot of this type of thinking in Chem 30. Where you're either taking away electrons or you're taking away or putting in energy. Anytime you remove something, that's on the reactant side. Okay. It's going to take energy to remove an electron. You take away an electron, and it's going to be positive now. Okay. We're doing all this in the gas phase, which should look a little weird. And we've removed an electron, so we see it as a product. Okay. You gain something, it's a reactant. You lose something, it's a product. So that's what the ionization energy 1 would look like. Okay. Okay. There's where our kilojoules would come from, and would have to remove 1 whole mole. You could calculate a second ionization. We'll talk about and make some predictions on second ionization. In short form, I'd call this IE2. Removing the second electron, we've got to start with our aluminum having already lost the first, so it's positive. We're going to need more energy, the energy required to remove the second electron. You remove an electron, and it goes from +1 up to +2 as you take away a negative charge, and you're going to get that second electron. Now, from +1 to +2 is the removal of a single electron, and that's how we'd define the energy for the second removal. We're not going to be predicting the kilojoules per mole. We're going to be comparing different metals. What would have a higher ionization, what would have a lower. We're going to look at group trends, and we're going to look at period trends. Now I'm going to put up those 2 parameters we tend to look at. Same in the previous lesson as this lesson. Okay. We may want to look at the number of energy levels, so kind of how big is an atom. Okay. Something, if it's really big and the electrons are far away, then they're not that attracted to the nucleus. They can be picked off or removed a lot easier. Something, if we have a really small atom, small distance between the positive middle and the negative outside, it's going to be harder to pull an electron away. Second thing, if we're in the same energy level, we would look at, well, what's the Z or Z effective? What's the proton count? Okay. So you can think of that as Z or Z effective. Okay. Z effective would be better to use, but we just look at the charge, the charge in the nucleus, the proton count. Okay. So same logic, same thinking that we would do to figure out atom size or ion size. So let's take a look at the trends across period 2. So we've got lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And we want to think of what sort of controlled variables, what is changing or manipulated variables. Well, we're in period 2. We're in the second energy level. So we're not changing energy levels. That's not a big difference. There's not a massive size difference. So we would want to focus in on what's going on charge-wise. Okay. Think what's going to be the easiest atom to pluck off an electron. Okay. So I'm going to put the Z's underneath the atoms, or at least for a few of them. If we look at lithium, it's atomic number 3. It's got 3 protons. Okay. So there's 3 protons holding on that valence electron. If we go to the other side, the other extreme neon, that's atomic number 10. Okay. Now we used this same type of logic before, or thinking neon's got more than triple the protons. More than triple the pull holding in a valence electron. So it's going to be way easier to pick off an electron in lithium. There's less pulling it in. Okay. Similar distance, much less attraction. So we're going to have a low ionization energy here. Small amount of energy is going to allow this electron to be removed. With neon or noble gas, it's going to take way more energy to pull that electron away. Okay. In this case, over triple the protons. So in terms of ionization energy, it's going to increase. IE1 is going to increase as you go across, and Z gets bigger and bigger. And that would be true in any period. Period 1, 2, 3, 7, as you go across, it's going to get harder to remove electrons. Lithium is so reactive, and all the group 1s are so reactive, you can't even let them touch water. Just liquid water at room temperature will allow lithium to give up that electron. Okay. Where you move over to, oxygen or noble gases, they're not very reactive. They don't give up electrons very easily. It's almost impossible for these guys to give up electrons. It takes too much energy to remove an electron and make cations out of our nonmetals. Now our metals, we're used to those becoming cations. That's kind of in science 10. Our metals become cations, or nonmetals don't. They become anions. It's because of ionization energy. And these group 1 is the easiest, group 2 is the second easiest. Okay, so that's our group trend. As you go to the right, it gets harder. Okay. I'm going to add to this. We've got our period. We go down the group: lithium, sodium, rubidium, cesium, francium. Now we've got different energy levels. We're not going to focus on Z here. We're going to look at lithium is the smallest, sodium is bigger, rubidium bigger, cesium bigger, and francium the biggest of them all. Francium's valence electrons are really far away from the nucleus, particularly relative to lithium. Okay. Francium's protons don't have a lot of effect, or near the effect, on those valence electrons. So in francium, that electron is so far away, it's picked off with little to no energy required, okay, compared to lithium. It's going to take a lot more energy because of distance. Okay, lithium 2 energy levels, francium 7. Okay. So francium is the easiest. It's going to have a low ionization energy. So ionization energy is going to increase as you go up. Okay. So high ionization energy, go up and right. Low ionization energy, go left and down. Francium being the extreme okay, or particularly the extreme of all our representative elements. Okay. Okay. It's not even stable enough to have, it's going to francium isn't stable and it's going to ionize really quickly. You're going to have a problem keeping neutral francium and not have it give up that electron. Okay. So that's our first ionization energy. Last little bit before I move into electron affinities, looking at removing 1 versus 2 electrons. Okay. Looking at when we get big differences in the second ionization energy, and I tend to put this on quizzes and on the chapter test. Let's look at beryllium versus lithium. And what would happen if you try to remove the second electron? This is really going to hinge on, are you removing one of those outer valence electrons, or are you removing one of those inner core? If we look at beryllium, so it's atomic number 4. It's got 4 protons, 2 energy levels. Lithium, atomic number 3. It also has 2 energy levels. Beryllium, the atom, 4 valence. Lithium, just 3. Now we're asked to compare not the first, but the second ionization energy. So the first ionization energy would be getting rid of the outermost. So that would be the outermost in lithium. That would be one of the outermost. So that's IE1. Okay. That's not what we're asked to talk about. We're going to look at IE2. Okay, so that one would be the ionization energy 2 for beryllium. It's one of the second energy level electrons. It's one of the valence ones. If we look at lithium, we have no more n equals 2 electrons to remove. We got to remove one of these cores. IE2 is a core electron. IE2 for beryllium was a valence electron, an outermost electron. So which is going to have a higher second ionization energy? It is going to be lithium by a country mile, by a huge amount. Removing cores take huge amounts of energy. So we're not using one of those kind of energy level or Z type trends with this. We're looking at valence versus core. So you could see this type of question show up comparing IE2 versus 3 or 1 versus 2. If there's a core versus a valence removal, there'll be a big difference. Lithium, if you look at questions, you'd want to look at how many valence electrons are you given in a question. 1 in lithium, 2 in beryllium. So that's ionization energy trends. Okay. So that is losing electrons. We're going to look at the gaining electrons, electron affinity or attraction to end the unit. So I'm going to use a generic symbol. I'm not using an atomic element here. I'm just using a generic Y. Okay. I'm not going to write out that same definition, but you need to have some element in the gas phase. And we're not looking at losing electrons. We're looking at gaining 1 mole of electrons. What's the affinity or attraction for electrons? And attraction of electrons, you would be getting an anion. No, I didn't put the energy term in. Energy can either be required or produced. With ionization energy, you always need a little bit of energy, or a lot. You need to input some energy to pull it out. With gaining electrons, sometimes you need energy, and sometimes it's a spontaneous release of energy. So the sign can flip either way. If you need energy, energy would show up as a reactant. If energy was released, then you'd see the energy term as a product. Okay. So I'm not labeling it because it depends on the circumstance where it would put the energy. Okay. We're going to talk about period trends, and we're actually only going to do period trends. So we're back to trends, we're back to those two things. We look at energy levels and we look at Z effective. We're going across a period, so the energy level is the same. It's period second energy level. So we look at Z, and we're going from 3 protons in lithium to 10 in neon. I'm not going to label that again. You may want to put in those Zs, or you've been writing in a lot, you might leave them out. Okay, so lithium 3 protons, neon 10. So what's that going to do to the attraction of electrons? Okay. We've got 3 protons in lithium trying to attract an electron. We've got 10 protons in neon trying to attract an electron. Well, 10 protons in neon is going to have a way bigger attraction than lithium. Or certainly as you go across, we're going to see an increased attraction. Okay. Now we're going to have a little quirk. We got to deal with neon sort of at the end. So as we go this way, because of more protons, we're going to see an increasing ionization energy. Sorry, increasing electron affinity. My brain's still stuck on the previous term. Okay. Now this increased ionization energy is positive or a release in energy. So the electrons want to take in the electrons. Okay. It's a spontaneous energy releasing process. Okay. And it more and more wants to do it, and you get a more and more positive number. There's a greater electron affinity. But it actually stops before you get to neon. So you'd think neon with 1 more proton would more want to attract an electron, but something happens when we get to neon. And any thoughts about what is different about neon in terms of that second energy level and room for another electron? Neon's already full. When you get to neon, 1s2 is its core, 2s2, 2p6. There is no room for that extra electron. So that's why you see the trend stop. If you want to add an extra electron, you'd have to actually add in a 3s1 electron. You'd have to go a whole nother energy level bigger. So that's why the trend stops. With fluorine, that's 1s2, 2s2, 2p5. There's room to add in another electron and go 2p6. Okay. Everything from lithium to fluorine has room in the second energy level to add in another electron. So you work your way across, there's room, lithium to beryllium to boron to carbon, and there's a greater and greater energy release, a higher electron affinity, all the way to fluorine, okay, which of the period has the greatest attraction, and then bang, it stops with neon because there's no more room. It'd have to go to a bigger energy level, and the electron affinity flips to be negative. It does not want an electron. You have to force it in. force it into that higher energy level. Now, the trends up and down aren't consistent, so we're not going to do group trends. The very generalized trend for this grade 11 course is that as you work your way across, the electron affinity goes up until you get to the noble gas. And it doesn't make a big difference how high or low you are in the table. We're not going to go into that. Your textbook dives into a little bit, okay? But if you compared beryllium versus antimony, okay? Antimony is a little further to the right, so you'd expect a higher electron affinity. So don't look up or down, just look right to left. The more right you get, the greater the electron affinity. And this will be a good vague prediction. Okay. So chlorine would be much higher than boron would be. Okay. Different periods, we got a right to left difference. Okay. So ionization energy, you're going to consider both periods and groups, electron affinity, just period trends. Okay. And that wraps up, this is our last lesson on the atom unit.